Okay, let's take a look at phase transitions. All right, so transforming from a solid to a liquid, liquid to gas. Again, we did this in the beginning, but let's do it. So going from solid to liquid to gas. Do you remember all of these transitions? Do you remember going from solid to liquid, liquid to gas, gas to liquid, liquid to solid, and then solid to gas, gas all the way to solid? Can you come up with those? So pause it and give it a try. But solid all the way to gas, sublimation. Gas all the way to solid, deposition. Solid to liquid, fusion or melting. And liquid to solid is going to be freezing. Liquid to gas, vaporization. Again, evaporation is not really, because that usually just refers to water, but vaporization is more correct. And then condensation, going from gas to liquid. We know that there are energy changes associated with phases. So going from solid to liquid to gas, or going from liquid to solid. So for gas to liquid to solid, so basically in the other direction. Think about sweating. You sweat to cool yourself down. You create liquid water in order to, and when it evaporates, so evaporation or vaporization is an endothermic process. So this is endothermic. And the one below is exothermic. Okay, so we have to know those phase changes and their energies associated with them. And we did look at enthalpies associated with these. So endothermic process is going to be a negative delta H, or I'm sorry, positive delta H. And a negative delta H is exothermic, okay? Endothermic is going to absorb energy. And exothermic is to release energy. So there we go. Good, okay. So if we take a look at all of these phase changes, what we do see is, again, we notice that the red is, again, heating up. It's going to cost us energy. Enthalpy is increasing. It's going to cost us energy to sublime something and to vaporize something and to melt something. And then condensation, we notice those are delta H negatives. But what you will notice is that again, this is Hess's law at play. Again, Hess's law, which states that I don't care about the method by which that I do this. All I care about is the end result, where I start and where I end. It's a state function. So the delta H of fusion plus the delta H of vaporization, again, fusion going from solid to liquid, and then vaporization going from liquid to gas, is equivalent to the enthalpy of going from, or enthalpy of sublimation, going from solid directly to gas. So those two things are equal, okay? And that's what you notice here is this plus this equals this, which seems to make sense. But again, we have to recognize that there's no loss in energy. There's a state function. So we can look at those in a bunch of different ways. Okay, good. So here's my vaporization, condensation. Not really a ton to say about this, other than there's an energy associated with vaporizing. And most importantly out of this is that we have vaporization. The negative is the condensation. So going in the other direction is endothermic, in the opposite direction, or exothermic in this case. Okay, so vaporization enthalpy is equal and opposite to condensation enthalpy. And yeah, I think that's good. So to vaporize 50 grams, this is just dimensional analysis. 50 grams requires 9.69 kilojoules at the normal boiling point. Calculate the molar vaporization enthalpy. So your answer, molar vaporization enthalpy under these conditions, molar vaporization enthalpy means it's going to be kilojoules per mole. That's the, if it just said vaporization enthalpy, you just calculate the energy, but molar is going to be per mole. So figure that out. How much energy was released? How many moles did you do? I mean, that's pretty much what you're going to do. And remember, vaporization enthalpy is delta H. Heat is going to be in Q. Carbon tetrachloride, you should know, is CCl4. But yeah, that's what we're looking at. So give that a go. We'll give this a try in class. So let's take a look at vapor pressure, because I mentioned it above when we talked about boiling, but let's talk about what vapor pressure actually is, because this does play a major role in this. So first of all, dynamic equilibrium. And this is the first time we're going to see equilibrium, but it's always going to be the same idea. The system will establish a forward and reverse process at equal rates. So there is ultimately, what it looks like is there is no net delta, no net change happening. So the dynamic equilibrium, there's no net change that's occurring. The molecules are moving around and everything is changing, but it looks like nothing is happening. This is typically called, we do call this the bathtub model. So if you imagine that you had a bathtub, it has a drain out and it has this little faucet in. Okay, so you're going to have water flowing in and you're going to have water flowing out. At some point, if you have the amount of water in equals the water out, you have now reached equilibrium. Reaching that equilibrium is bathtub model. So that's a dynamic equilibrium. Molecules are constantly changing. We're losing molecules, we're adding new ones, but it looks ultimately like everything is remaining constant. Okay, so that is what a dynamic equilibrium is. And vapor pressure is something that forms a dynamic equilibrium. It is the pressure. Again, pressure is just a force. The force of vapor when liquid and gas are at equilibrium. So if you imagine that we have some gas, and right now it was just placed in there under a vacuum. So we have this liquid and no gas particles, and then we allow it to reach equilibrium. So we have a bunch of these things that are going to fill the headspace. Have you ever taken a container and sealed it up? Right. And so something volatile like a nail polish remover or something, and you open up the top, or a candle, maybe that's a better example. This even happens with solids, believe it or not. But you open up the top and you smell it and it's very potent. But over time, over a couple of moments, it's no longer as potent. But if you seal it up again and allow those vapors to fill the air again, and you take it off, you're going to have that same smell, or you're going to have that same intense thing, because given time, if the seal is broken, those gas molecules are escaping. But if you seal it up, it's going to reach this equilibrium where there's a certain number of gas molecules in that space. So once it reaches equilibrium, notice that it has actually pushed down this mercury and reached an equilibrium. So over time, they will always reach this kind of equilibrium. And how this is done is through looking at kinetic energy. So if you look at kinetic energy of low temperature or high temperature, it doesn't really matter. If you look at kinetic energy of a bunch of molecules, what you see is there is a bunch of them that are moving very fast. There's a bunch that are moving very, I'm sorry, I should say it this way. There's a bunch that are moving very slow. The average have a very low kinetic energy. And then there's a bunch that are very fast. And then you have a ton that are right here in the center. The ones that are beyond this minimum kinetic energy point, these can all can escape into the atmosphere, can escape into the gaseous phase. So if we look at the proportion of molecules that can get into the gas phase at low temperature versus the proportion that can at high temperature, that makes sense that we have a higher vapor pressure because you have more of them getting into into the gaseous state. All right. Again, it's gas beyond that part and it's liquid below that. So the higher the temperature, the more that flattens out and the more molecules you have, the higher the vapor pressure that you have. Bring this all back. If I increase the intermolecular forces, they're held together better. Therefore, we get a decrease in vapor pressure. So we have really low vapor pressures for things that hold together very well. But if I increase the temperature, we're going to flatten out that curve. We're going to see an increase in vapor pressure. So that's kind of the, that's the quick summary of all of this conversation. All right. So vapor pressure and intermolecular forces. Again, looking at intermolecular forces, we know that boiling point is a good measure. So boiling point is equal to where the vapor pressure is equal to the atmospheric pressure. So normal boiling point, anything that is the normal boiling point is usually at standard temperature pressure. So in the case of normal boiling point, it's at the boiling point at 1 atmosphere. Again, 1 atmosphere is equal to 760 torr, which is equal to 760 millimeters of mercury. And those are the ones that we typically use. So if we look at this equation right here, if we look at this graph right here, what do we see? So here is my normal boiling point. Okay, so, or my standard pressure. So this right here is the normal pressure, right? 760 torr, 1 atmosphere. And these values right here are going to be our normal boiling points. Right. And what do we notice? Well, diethyl ether looks like this. Ethyl alcohol looks like that. Water looks like this. Maybe I should figure out which one is the strongest. This one has London dispersion forces and dipole-dipole. This one has hydrogen bonding. This one has even more hydrogen bonding. So we expect this, then this to boil, and that is in fact what we see. But what we do notice is as the pressure decreases, again, as the force pushing down decreases, we see a lower boiling point, okay? Why is that? Well, it's because things, again, if we're looking just in terms of the amount of pressure pushing down, right? So if this is my liquid, the amount of pressure pushing down from the atmosphere, if that decreases, because we go to a higher altitude, the amount of energy I have to push back with is lower, and therefore the boiling point drops. It's really hard to boil things in Denver. So in Denver, at a pressure of 0.817 atmospheres, water has a boiling point of 95 degrees Celsius. 5 degrees is a massive difference, okay? And then I've been avoiding this, talking about it, but it's pretty straightforward. Something that is volatile has a high volatility. Has a really reduced vapor pressure. It's a measure of how easy it is to vaporize something, usually a liquid. Volatile organic chemicals is kind of a thing. So it's the things that makes them easy to jump into the gas phase. Whenever you're looking to buy like paint or something like that, they talk about the VOCs. So the higher the volatile organic chemical is, basically the more VOCs is, the more smelly it is going to be ultimately. And the quicker it's going to basically evaporate. All right. Clausius Clapeyron equation. So we're quickly going to kind of cover this idea. We're not really going to get too much in detail over this. So I just want to present this idea because I don't think you really need to know it as much. But the Clausius Clapeyron equation. So it is the quantitative relationship between vaporization enthalpy, vapor pressure, and temperature. So we have this equation right here. C is a constant. R is our ideal gas constant for energy, because energy is involved, 8.314 joules per mole K. Okay. It is not equal to liter atmospheres per mole K because there's no pressure involved. We have temperature. Again, it's going to be in Kelvin. Vaporization enthalpy generally in kilojoules because it has to match, or actually better off in joules because it has to match the R and a bunch of other stuff. This is the one that I want you to know though, because this is where we're typically going to use it in this type of form. When we have two sets of pressures and temperatures, we have this Clausius-Clapeyron equation. When written out is, when rearranged, is y is equal to mx. So this is actually going to be a straight line, or should be a straight line. So if we look at the Clausius-Clapeyron equation, here's the Clausius-Clapeyron equation that I plotted. Your m, your slope, is going to be negative delta H of vaporization all over R. If we rearrange this, your slope times your R value is equal to the negative delta H of vaporization. So we can get delta H of vaporization if we have two different states. Okay. Okay, good. Just quickly, I want to cover this. Hopefully you remember this, but if I divide X over Y, if I take the natural log of X over Y in parentheses, it's equivalent to doing natural log of X minus natural log of Y, much like natural log of X times Y is equal to the natural log of X plus natural log of Y. So you can essentially distribute that. We would need that when you're doing natural log here. That's why I wanted to point it out, because when you do separation of those pressures, you have to, if you only have one pressure and you need to solve for it, you need to remember how to separate out a log. That's how you do it. Okay, good. So here's an example of the Clausius-Clapeyron equation. You have this situation, try it, CFC 11, have two different states. What's the new vapor pressure of C, or what is the vapor pressure of CFC 11? All right, next up, critical temperature and critical pressure. So the critical point is the point where liquid and gas are indistinguishable. From one another. So there is a minimum temperature that this occurs. There's a minimum temperature, and that is called the critical. There's a minimum temperature that this occurs at, and this is called the critical temperature. And so the critical temperature, again, or temperature where liquid can no longer exist. Regardless of pressure. The increase in pressure, we can see it as kind of forcing molecules together, but there's a certain temperature where that just doesn't matter how much pressure you apply. This is known as TC, pressure critical. It is the vapor pressure at TC. Okay, again, intermolecular forces versus pressure and temperature. We're going to take a look at this next as well. All right, next up, melting and freezing, again, equal and opposite. That's really kind of what I'm pointing out here. And then the heating curve. So the heating curve is an important thing. The heating curve is an important concept. So the heating curve, we have two things. I have temperature and I have heat. Okay, again, it's going to cost me energy to melt or to bring to heat up a solid. When we have these solids. So we have a bunch of different regions of this thing. So the way to look at this is get those perfect lines here. That's enough. Each time you see one of these transition parts, so each of these moments in time, we have a different thing that's going to govern the temperature change. So if we just think about in terms of, we have solid to liquid to gas, in between these, we have solid and liquid together, and we have liquid and gas together, okay? So these things are governed by how much heat. So when we're heating up a solid, we are using, and we already know this, Q is equal to the specific heat times the mass times delta T. When we are heating up when we're going through a phase change, we're looking at the delta H times the number of moles, okay? And that's it, ultimately. Every single time you heat a substance up when it's in one phase, you're using that equation. And every time you heat up, to go through a phase change, you have to use the enthalpy of the phase change. So again, we already know these. So C is specific heat. M is mass of that substance. T is delta T, right? In this case, delta H is going to be the enthalpy of fusion or freezing. Yeah. And N is moles. So that is the calculations that we do. We have to add a bunch of different energies. Let's see here. Yeah, so how much energy is absorbed for the release of 65 grams of water heating from -15 to 47. So we have a change in temperature. We're going from -15 to 47. So think about where that is. -15 to 0, 0 to 0, and 0 to 47, or I guess down here, 47 degrees. So there are 3 steps there ultimately to tell you what the energy is. So we're going to calculate this together as well. And then we're going to move on to phase diagrams. I like phase diagrams. They're actually pretty nice.